When an object travels in a straight line, it has momentum, given by mass times velocity. If that motion becomes circular, we can talk about the angular momentum of the object. The size of the circular path becomes important, and we define angular momentum L as radius times mass times velocity. It's helpful to express this in terms of rotational quantities, too. Let's write the tangential speed in terms of the angular velocity omega. With a slight rearrangement, we can see that the remaining terms combine to give the moment of inertia of the object. Now, both of these are valid expressions for the angular momentum, but in the first case, we treat the object as a single point mass. On the other hand, 2- and 3-dimensional objects can be described by a moment of inertia, and we saw earlier that when they spin, the angular velocity is a value that works well for describing the speed of the entire object. In some situations, the angular momentum of a system can be conserved. A great example is the case of a spinning figure skater who can change their speed by extending or tucking in their arms. When a skater brings their arms into their chest, their mass moves closer to the rotation axis. This decreases their moment of inertia, and since the angular momentum is conserved, the angular velocity will increase in response. Here's another example of conservation of angular momentum. Suppose your friend is trying hard to bring back the 1970s by breakdancing, and you need to let him know it's not working. While performing a backspin at a certain angular speed, you drop a tie-dyed beanbag chair on him. If we think of your friend plus the beanbag as a system, we can equate the total angular momentum before to the total angular momentum after. With the extra mass of the beanbag chair, the moment of inertia is going to increase, so you would expect that the final angular speed will decrease.